Thank you. Thanks for watching out for me, Sarah.
Hey, keeping you honest.
Yeah, thank you. So that's the poll results. You guys see that, I assume, maybe. You're interested in the different aspects. Always my favorite is my boss told me to attend. That's good. So we have interest in soil management, and the tri-states are very popular, a reason for being here. So anyway, that's great. Great. So again, this is the soil fertility presentation. We have one next month on soil health. And then in February, we're going to have a presentation on cover crops. So and then we go into March is on dollars and cents, I believe. And then April's on some decision making in the watershed, if I'm not mistaken. So we have a full rest of this winter covered schedule. So on your Tuesday mornings or whatever day this is, you can
Can we please not go back to Tuesday this week? It's already Thursday.
Thursday, okay. So we'll have the dates are out there for you. So we'll have a first of the month session every month to learn a little bit more about what's going on with the project. So with that, let me start this video. This is our first one will be on soil sampling, and there's been some interest in soil sampling, so we put these together with Jason Ackerson. Jason Ackerson is a new professor, newish professor at Purdue, and he is an expert in soil sampling and dimensions related to soil sampling, how to use soil sampling data, how to arrange for soil sampling. So we got him involved in this and let him talk a little bit about soil sampling, and I'll start that up right, I hope now. Everybody hear it okay?
No sound.
No sound?
Not for me. Did you click the little boxes when you shared video that said share sound?
I thought I did.
Hello, I'm Dr. Jason
Oh,
Anderson.
I heard that
I hear a little bit.
right at the end.
For reliable soil tests. Now, in only 5 minutes, I don't have the ability to get into all of the different nuances around various soil sampling programs and soil sampling ideas and concepts. What I do want to do is spend a brief bit of time.
All right, so now rewind and share your screen again.
Around why.
Share your screen. Share.
It was shared. I don't understand what the hell.
You unshared somehow.
All right. Let me try this again. It's supposed to be shared. I don't quite understand why it's not. Here we go. Hold on.
Hello, I'm Dr. Jason Ackerson, a soil scientist at Purdue University. Today we'll be talking about soil sampling for reliable soil tests. Now, in only 5 minutes, I don't have the ability to get into all of the different nuances around various soil sampling programs and soil sampling ideas and concepts. What I do want to do is spend a brief bit of time explaining to you some of the core ideas around why our soil sampling guidelines and recommendations look the way they do, and hopefully give you some perspective on how to take those concepts and ideas and apply them to developing your own soil sampling management plan. So the reason we need a soil sampling strategy or a science-based approach to soil sampling is because soils can be incredibly variable in small scales. So the map you're looking at is a digital soil map of phosphorus content for a field in Illinois, and this field is roughly 40 acres in size. And you'll notice the background colors denote the range in soil phosphorus test levels across the field, with green colors denoting areas of high phosphorus north of 40 ppms, with the sort of peach and lower colors, the sort of tan colors denoting lower levels of phosphorus. So given this information about how we think soil phosphorus might vary in a field, we can use this data to sort of illustrate some of the key concepts and points around soil sampling. So in soil sampling, we often try to use what we call a composite sample. And this would be a sample that is made up of soil samples or soil cores collected from multiple areas in the field. And the size or number of samples that go into that composite can greatly impact the reliability of that soil test. So given our map of soil test phosphorus for the area, we can actually simulate a bunch of different soil samples. So we can choose a random set of points and estimate what their soil phosphorus level would be at those points, and estimate what the final soil test value would be if we added all of those points into a composite. So here we're showing 3 points, each denoted by the black dots on the screen. And those black dots we can think about as places where we would go and collect a composite sample. So we go to each of these points, collect the soil core, mix it into a bucket, and send that single sample to the lab. Now we can measure what that sample would be and compute it on a chart. And what we'll do here is I'm going to show you a bunch of iterations of potential soil samples from that field, and we'll look at the final resulting collection of soil tests. So here we're showing another group of 3 sets, and these are all estimated or located in random points. Here's another set of 3 points, and here's a final set of 3 points. So if we do that sort of exercise of collecting 3 random soil cores from this field and generating that composite, and we do that hundreds of times, we can estimate the range of potential soil test values for that field. And that's denoted by the box plot here on the right. So you'll notice that the box plot spans from around 22 ppm to about 35 ppm. So you can think about each of these breaks in that box plot representing areas of equal probability for that soil test. So if we were to collect any random set of 3 points from this field, we'd have an equal chance of getting a soil test value between 22 and 25 ppm as we do a soil test value between, say, 33 and 35 ppm. So what we're noticing here is that with only 3 points, there's a 22 to 35 ppm range in potential soil test values we could get. Now that has big implications for thinking about your fertilizer program. A value of 22 is going to see a much lower demand for crops than a value for 34. So on the previous slide, we saw how soil samples that are derived from a composite of only 3 sampling locations can provide a very large range of potential soil test levels. So one obvious solution to that is to collect more composite samples. So we're going to do the same set of simulations now, but instead of only using 3 samples, we're going to double our sample size to 6. So here we're showing a set of 6 randomly selected points. Again, each of these points represents a place where we're going to collect a composite sample. And we'll combine those composites to get a realization of a potential soil test level for this field. And again, just as we showed on the previous slide, we can iterate that same sort of sampling program hundreds of times, and we get a resulting soil test level or population of soil test levels. So now we're showing a box plot where our potential soil test values, now instead of ranging from 22 to 35, range from somewhere around 26 to around 34. So by doubling the amount of composite samples in our final soil test, we get a much more reliable soil test where the potential range of soil test values is much smaller. So what this means is that as we increase the number of composite samples in our soil sample, our soil test value or the variability of that final soil test becomes even smaller. So we have smaller soil variability or a more reliable soil test as we increase the number of composite samples in that resulting soil test. So as we talked about in previous slides, as we increase the number of soil samples going into a composite, we end up with a more reliable soil test, or one that has a smaller variability or potential range in our soil test value. And taking that to sort of the logical conclusion, as we increase from 3 to 6, now to 12 soil samples, you'll notice that the soil test value or the variability in soil test values has decreased even more significantly. So we can look across all 3 sample sizes here denoted on the right-hand set of box plots, and we'll notice that the average soil test level, or the black line, doesn't change across all of our soil tests, but the reliability or the variability from test to test increases. So the take home from this is that as we increase the number of composite samples into any single soil test, the variability of those test results becomes less. So if we're comparing one sample to the next, maybe this is a sample from 1 year to 2 years from now, we're more likely to see consistent results if we collect more composite samples. So on the previous set of slides, we talked about how increasing the number of soil samples in a composite sample improves the reliability of the soil test and decreases the variability from test to test within a field. Now we can achieve the same outcome by actually testing on smaller areas. So on the map, I've outlined an area in a black square which represents a 5-acre subsection of the field. And this is analogous to what people do when they start zoning or gridding fields out. So we're going to sample a smaller area of the field and actually do the same exercise we did on the previous set of slides, but now in a smaller area. So for the sake of time, I'm not going to show animations for every simulation we've done, but suffice it to say, we did essentially the same set of simulations, but instead of a 40-acre section of field, we've used just the 5-acre section of field. So what you'll notice, and I think the most striking result from this, is that when we've decreased the size of the field that we're sampling to 5 acres rather than 40 acres, the range of soil test results across all sampling sizes is decreased. And in fact, if we compare the range or the variability of soil test results for the 3-sample composite on this 5-acre section of field, it's about the same as the range of soil test results that we saw for the 40-acre section of field. So the conclusion to that is really that sampling size, or the number of soil samples in any composite, has the same effect as decreasing the area that you're sampling. So increasing your sampling size or decreasing the area that you're sampling will both decrease the test-to-test variability in your data or improve the reliability. And this should make sense, right? As we're sampling a smaller section of field, we're sampling a more homogeneous bit of soil, and it's likely to have more consistent results from test to test. So to recap, increasing the number of soil samples in any given composite sample will decrease the sample-to-sample variability and improve soil test reliability. Essentially, more soil samples improves the reliability of our soil test. The same can be said for decreasing sampling area. By decreasing our sampling area, we can increase the reliability of those soil tests by decreasing the sample-to-sample variability. So in summation, designing a soil testing program requires that you think about both the effect of sample size, or the number of soil composite samples in a single soil test, as well as the area you're sampling. So if you want the most reliable sampling data, you either need to increase your sample size or decrease the area that you're sampling. Now, I haven't had the time to get into all the nuances of different sampling strategies, but if you want more information on those, feel free to reach out to a cooperative extension agent in your local county or send me an email directly. I'm sure they'd be happy to help you out with designing a soil sampling program that's reliable and effective.
All right, that was Jason Ackerson. He's our soil he's our soil handling expert and works in soil properties. He's a relatively new, recent hire. He's very reachable at Purdue. If you want to get hold of him, let me know. Are there any questions on soil sampling we can try to answer? Jim's on the line, he can help, and Ben's here. So everybody seeing the video okay? All right. Good. All right. No questions? All right. Let's move on. Jim Cambarato was kind enough to put together a video for us as well. If I can figure out where I put it, there it is. And Jim's going to talk a little bit about the tri-state recommendations. And that's a very, very hot topic for us in terms of they haven't been revised, and I think that it's 25 years. So we've had a lot of interest in the revision of the tri-states, and Jim has been very active in that process. And he's a co-author on the recently released report, and he's going to be here talking to us a little bit about it with this video. Let me get the screen share going, and make sure I have the sound turned on for everybody who cares about those kind of things. And then we go from there. Going to share and go.
Hi, my name is Jim Cambrato, and I'm a soil fertility extension specialist in the Department of Agronomy at Purdue University. And I'm here today to talk to you about an update to the tri-state fertilizer recommendations that became available in November of 2020. The last version of the tri-state fertilizer recommendations was published in 1995. So it's been quite a while for an update. I'm going to highlight some of the changes related to both nitrogen and phosphorus, the two nutrients that have the most environmental impact when they leave the field. Let's get started with nitrogen. This is something that we've worked on since about 2006, and we actually started using in 2010 or so. However, it was not formalized in the tri-state recommendation bulletin until now. And the current recommendations are based on numerous experiments conducted around the state, whereas the previous recommendation system was somewhat theoretical, based on expected yield and various factors that we'll talk about just briefly. The original recommendations were yield potential based, so the farmer would predict the yield that would be made on the field and then multiply that yield times a nitrogen factor, which was 1.36 pounds of nitrogen per bushel. So what they were doing was predicting how much nitrogen would be in a crop at a certain yield level at the end of the season. And then they would subtract off an estimate of what the soil would provide, which was 27 pounds of nitrogen per acre for corn after corn, which is a pretty low value. And then if they were in rotation with soybeans, they'd subtract another 30 pounds of nitrogen per acre. This was a pretty simple, straightforward way of making a recommendation, and it makes a lot of sense to a lot of people because higher yielding corn is generally larger and it likely contains more nitrogen. Despite making sense and being easy to use, we found it has actually no relationship with the fertilizer nitrogen rate that is needed. So the yield achieved is not related at all to how much fertilizer nitrogen needs to be added. And this is probably because of that estimate of soil N is very hard to predict. And 27 pounds of nitrogen per acre is a really low estimate to begin with. So we found we needed to develop another way of making nitrogen recommendations. And the way we did this was to conduct a lot of experiments. So current recommendations are based on about 200 field scale trials and ranging in size from 10 to 50 acres, where we would apply 5 or 6 N rates replicated 4 to 6 times across the field. And in the background photo, you see a picture of a nitrogen trial, and the different colors of green represent the different nitrogen rates. And as you know, the lower the N, the yellower the corn, and the higher the N, the darker green the corn. So we conducted all those experiments throughout the state of Indiana, and we came up with recommendations based on the results of those experiments. You see here a map of Indiana with the physiogeographic regions, so the different parent materials that resulted in varying types of soils. And we found that in the western and southern Indiana that the nitrogen rates needed to optimize yield were in the range of about 175 to 180 pounds of nitrogen per acre. And then in the eastern and central Indiana, we found the nitrogen rates to be a lot higher, 195 to almost 220 pounds of nitrogen per acre. And there's two bars on that figure. The blue bars represent the average N rate we found to maximize yield, and the green bars represent an estimate of the economic optimum N rate. We can't really fertilize for maximum yield unless we want to lose money. So we use the price of corn and the price of nitrogen fertilizer to calculate the economic optimum. And that's what we suggest producers aim for, is that economic optimum N rate. So in the area that's most interest to you in the northeast Indiana, we found one of our highest economic optimum N rates. And that's because many of those soils are very poorly drained. And so the soil contribution is actually reduced by that high moisture. The nitrogen that's released from organic matter is less because the soil is less oxygenated because it's wetter. And then also the nitrogen that's added, if rainfall is high, is also lost at a higher rate because of denitrification and gaseous losses of nitrogen from the soil. If you want to read more about our recommendations, how they were built, and other aspects of nitrogen management, the extension piece on the left, Nitrogen Management Guidelines for Corn in Indiana, is available at the URL shown. And we update that periodically, almost every year, and it'll be at the same URL every year. So you can go back and look at it next year or the year after and see if it's been updated and what the changes have been. If you're interested in using a calculator to determine what the recommendation is based on price of corn and price of nitrogen fertilizer, the URL shown with the map on the right will get you to a calculator where you can input the prices of corn and fertilizer and the region that you farm in, and it'll give you the recommendation. All right, let's turn our attention to phosphorus. Of course, another nutrient that when it leaves the field can affect water quality. Currently, in the new updated tri-state, the recommendations for phosphorus fertilization are going to be made based on a Malic 3 ICP extract. So that's the method of soil testing that's used to remove phosphorus from the soil, and then the ICP refers to how it's measured. In the old tri-state, the phosphorus recommendations were based on a method called Bray P1 colorimetric. Both methods are excellent for making fertilizer recommendations, but they remove different amounts of phosphorus from the soil. Malic 3 ICP removes inorganic phosphorus as well as some soluble organic phosphorus. So its numbers are going to be higher than the Bray P1 colorimetric because that only measures the inorganic phosphate that's removed from the soil. Both are highly correlated and excellent for making recommendations, but if you switch to a lab that's reporting the new method, then your numbers will be higher than they have been in the past. So you have to keep that in mind when you're comparing your new soil test results to the old soil test results. Laboratories have actually been using the Malic 3 ICP method for 20 to 30 years, but they were converting the numbers they got to the Bray P1 colorimetric because that's what our tri-state recommendations were based on. Because they remove different amounts of phosphorus from the soil, that means the numbers that we use for the critical level and the maintenance range change, and I'll show you those in a minute. Probably the most impactful change is that the fertilizer recommendation now goes to 0 at the maintenance limit, not the maintenance limit plus 10 parts per million Bray P1 or 13.5 parts per million Mehlich 3 ICP. And I'll give you a little more detail on that. And then the crop removal values for phosphorus have been updated, but for phosphorus the change is fairly minor. If you're interested in the changes in potassium, which were much larger and will alter the recommendation more, then download the new Tri-State and you'll see those crop removal values there. All right, so I told you about the new method, the Mehlich 3 method, and the phosphorus measured by ICP, which gives higher values than the older method, the Bray colorimetric. So if you have a Bray number from a past soil test, you would multiply that by 1.35, and that would give you an estimate of what your Mehlich 3 ICP number is. Or if you've gotten a recent soil test and it's done in Mehlich 3 ICP, then you would divide by 1.35, and that would relate to your older soil analysis that you might have from previous years. There's other conversion factors given there in case the lab that you use uses a different method or a different way of measuring the phosphorus. So you can convert back and forth from these values without much error. The estimates are pretty good because the methods are highly correlated. Okay, so now what I think is the most impactful change. This diagram shows the original Tri-State recommendation, which has 3 phases: the build-up phase at low soil test levels, the maintenance phase in the middle for moderate soil test levels, or optimal as it's defined in this figure, and then a drawdown phase at the high soil test levels. At the high soil test levels, because soil testing, soil sampling was done on a pretty coarse basis and fairly infrequently when those recommendations were put in place, the scientists that made the recommendations thought that it would be good to have a little wiggle room at the high end of the soil test level. And so they suggested some fertilizer P be added, but less than crop removal. And eventually over time then the soil test phosphorus levels would fall from the high levels down into the maintenance range. Because soil sampling is much more intense now and samples are taken more frequently and all the laboratories are doing an excellent job in measuring phosphorus, we didn't think this wiggle room was necessary anymore. And so the drawdown phase has been removed from the recommendations. So instead of the recommendation going to 0 at the high end of the drawdown phase, the recommendation goes to 0 at the maintenance limit. On this slide, I've written the new critical levels for the Mehlich 3 ICP method. 20 parts per million is the critical level, so from there to 40 parts per million, we recommend that crop removal be applied to maintain soil test levels in that range. And then below 20 parts per million, we recommend enough fertilizer be added to replace crop removal, maximize crop yield, and then a little extra over a 4-year period to build up the soil test to the maintenance range. We've always taken a very conservative approach to recommending fertilizer where there's little response to getting yield response to fertilizer in that 1 year, but it gives the farmer the flexibility to skip a year if the price of fertilizer is real high or the price of corn and soybeans is real low or the weather is just not conducive for making a phosphorus application. Whereas if soil test is low and yield decreases are going to occur because of phosphorus deficiency, then the penalty for having to skip a year is much greater. Okay, one last change. We've updated the grain nutrient removal values based on a lot of grain samples over the last 10 years. And for phosphorus, they haven't changed too much. For corn, instead of estimating about 0.37 pounds of P2O5 per bushel per acre being removed for every bushel of grain, the new estimate is only 0.35, a reduction of about 5%. In soybeans, there actually was no change. What we used as crop removal 25 years ago, we found to be just the same now. And then for wheat, the reduction has been somewhat larger, from 0.63 pounds of P2O5 per acre per bushel down to a half of a pound of P2O5 per acre per bushel, a 26% decrease. And this is what should be used, this value should be used to multiply times the yield and determine the fertilizer rate when soil test is in the maintenance range with those moderate or optimal soil test levels. At levels below the critical level, then grain phosphorus removal is part of the recommendation, but remember then there's the extra phosphorus that is added to build the soil test up to the maintenance range level. Now we're all concerned about phosphorus movement either down from the soil into tile drainage or in runoff from the field or in erosion and sediment that leaves the field. And it does happen at any level of soil test. But maintaining these levels of soil test phosphorus will have minimal impact on phosphorus moving to water. And so don't think just because we're talking about 20 parts per million or 30 parts per million that those are excessive. They will result in a little bit of phosphorus movement, but the amount leaving the field should be fairly small. All right, so that was just a brief update of the Tri-State Fertilizer recommendations that were released in November 2020 for Indiana, Ohio, and Michigan. You can download this document at the URL given, or you can order a paper copy for $9 a copy if you're interested. If you have any questions about what I talked about today or anything in the Tri-State Fertilizer recommendations, please do not hesitate to contact me at my email shown there on the slide. So thank you and have a great day.
All right. So Jim is actually here with us. If you have questions, he's here to help out and answer if he can. I'm sure he can. So anybody have any questions? There he is. I'll ask a question, Jim. What's been the reception to the new Tri-States? How they've been received?
Oh, I think they've been received well. People have been calling for them for a while because they thought the old recommendations were outdated. And it's nice to get all that information in one document now as well. So yeah, they've been received well. Hadn't heard any complaints yet. I'm sure they'll come. Eventually there'll be some complaints, but not yet.
Good deal. Other questions? All right. Well, with that, I will bring up our next presentation. It's by your host here, me. So I'm going to talk a little bit about soils, a little bit about frozen ground, and I have a study from Wisconsin. I'm going to one of my former grad students was involved with that. he gave me pieces of to show you. It's really interesting about how phosphorus moves in frozen frozen conditions. So it's a real interesting piece of work. So let me figure out what I did with it, and we'll go from there. Here we go. Okay. Good day. I'm Ron Turco. I'm the head of agronomy at Department at Purdue University, and by training, I'm a soil scientist and a soil microbiologist. Today, I want to talk a little bit about how soils behave and how temperature and soil water are related, especially when it's a little bit cold. This project stems from some efforts we've been running in the northeast part of the state, which we refer to as our St. Mary's Project, which is what brought you all here to begin with. But as part of the background on the St. Mary's Project, we've had a lot of support from a large number of ag industries in the state, including IANA, which is the Indiana Ag Nutrient Alliance. One of the key goals of IANA is, and the one we support, is eliminating as much as possible application of nutrients, including manure, to frozen or snow-covered ground. And I've been asked a number of times, why is the winter condition so difficult to deal with? So for the next few minutes, I want to help share some ideas, some things about go on in soil, how soil's formed, how that all ties together, and then look at the issue of frozen ground. I've also been very fortunate to be able to bring in, share a little bit of data with you from a study in Wisconsin where they took a very close look at frozen conditions and how that all comes together. So let's start out just a little bit of soil science. Soils are a complex mixture of minerals, water, air, organic matter, both dead and alive, and this sort of forms the surface of the earth. Soils not always existed. It's been created by a combination of actions and events through time, which basically take a rock and break it up into little teeny pieces, and then you have a little bit of microbial activity and get some plants growing in there, and it all sort of forms up into what we can sort of see as soil. The key part of that is that as soils form, they also form clays, and they structure themselves. They create, which is referred to as, they're sort of the tilth of the soil. So a lot of this was known, but it was a gentleman by the names of Hans Jenny in 1941 that published the first real look at how soils form, and this is sort of the underlying principle of soil science now is related to what Hans did back in the 1940s. So what is soil formation and why do we care? So basically, if you take that parent material, which in this case has got the big C written on the gray box, and then you go through cycles of heating and cooling and freezing and thawing, and you add a little water, and you basically break up that material, and it becomes smaller and smaller in pieces are basically acted upon by the environment, and you can start to form soils. And that's basically how our soils have formed in a very simplistic manner, much more complex in reality. But it shows you that as soils form, they create layers and horizons, and those materials are what we work with now today in agriculture. The part of Northeast Indiana, a major action that took place millions of years ago was basically the actions of glacial movement, which crushed rocks and materials, helping to form what's referred to now as glacial till. And then further development occurred in the soils of Northeast Indiana that resulted in the soils forming a clay material. So we have glacier till material, but it's also interlaced with clays up in Northeast Indiana. What that looks like, if you kind of take a look through the profile, you'll see layers of different colors and textures, and they form from the top down. So the top of the soil is where the organic matter accumulates. Water runs through that system. Those systems react to cold, to dry, to hot, to warm. It's all those different things going on that helps create that profile. inside of that soil, basically, is you have this thing called texture. And texture really is a look at the content of sand, silt, and clay that's in there, and that gives that soil that basic physical structure. So texture is what really controls a couple of critical things about agriculture. Texture is what controls water retention in soil. And as you get more clay content, you tend to hold more water in that soil. And if you think about it just for a second, tiling to remove excess water is in a lot of cases related to the presence of too much clay and that soil holding too much water. It turns out up in northeast Indiana, those are glacial till soils with a high clay content. So it's a very important condition that we take advantage of in many ways for agriculture, but also comes back when once things cool off in the winter, that water can freeze in that soil. So again, if you think about it for a second, small versus large. On the right side, you have what's micropores, which is what you'd see typically with clay, and then you would basically have a situation where that soil would have very, very small material in it. And that's basically what underlays much of what's up in parts of the state related to glacial till. And the glacial till basically in this case is formed to have a clay content as well. So if you look at a couple of maps of Indiana, you see up on the right side, you see a lot of orange up in the northeast corner of the state. And that's basically those glacial till soils and the blondes, the Poyamos, and the marly soils that are so common up in that region. These soils tend to have a little bit of clay content in them, quite a bit actually in some places, and that really dominates the features. On the left side of this figure, you basically see different lettering on there, which sort of again redesignates those kind of spots up in the northeast part of the state, and this is based around the presence of clays and till materials that dominate the features that we deal with. And the really interesting part about all this is as you move through different kinds of soils, which are across the bottom of this figure, you see gravel, sand, sandy loam, clay, clay loam. You basically see two inverted curves that are inverted each other, which is basically the one on the left is water movement inside of the soil, and on the right is basically water retention. As you move from gravels to clays, basically weathering materials, through time, you see that you can retain more water, but you move less water. So water stays in the soil. You basically have a condition where it would be poorly drained soil. Typical of how we'd respond, of course, is to install tile drains and to help manage that water removal from the soil. But let's put one more parameter into this, and that's basically cold. And once you get below about 24 degrees Fahrenheit, you basically have a condition under which the soil will be frozen. And at these temperatures, the ground freezes solid, and the depth of the freeze really is dependent on the duration and severity of the cold temperatures, soil moisture, and the soil type. So if you have a condition where you have wet soils that are frozen, that undergo freezing, you can have a condition where you basically put a big ice lens into that soil and influence what can go on the surface during the winter. And a good example of that is this picture here, is where you have you basically have frozen soil, which is designated by the gray materials, and on top of that you add water. The water is not able to penetrate the soil; it runs off. So basically, you create a very strong peak response, which is with the illustration on the right side, and that's it's called a hydrograph, which is basically looking at the rate of the water discharge, which is the Q value over time, and you see a very sharp peak, which is basically the water leaving the surface of that frozen soil because it can't get into the soil itself. Now let's throw one more little component on top of this, and that's manure management. So when you have manure, you basically have a very economical source of nitrogen, phosphorus, and potassium. You have a way of recycling these nutrients, and you have a way of managing a waste from a storage lagoon or someplace that you're raising animals on. But as you know, there's also a lot of rules related to the presence and use of organic fertilizers. This is a set of rules in terms of setbacks for during the normal part of the year, the warm part of the year, how far you need to be away from things in terms of manure applications. And then you throw in one more complexing feature. You throw in that old frozen ground and you have a different situation. You basically have conditions under which water can't enter the soil because the soil's frozen, and then you're going to up the opportunity for runoff from those soils, and you need to really think about how you manage that waste material in the winter. Again, going back to our IANA statements early on in this presentation, we tend to want to discourage the use as much as possible of frozen ground for the application of manures. Why? Frozen materials, frozen soil is not accepting for liquids. Tends to want to run off, tends to want to go move across the surface of the soil a little more than you would normally want. So I'm fortunate enough to have a former grad student by the name of Matt Ruark, who went on to work at the University of Wisconsin, who's involved in these discovery farm studies, where they've been looking at these same type of questions up in the Wisconsin region. A little bit colder up there, a little more significant freezing signature, but very similar conditions to what we have. So they wanted to look at basically how phosphorus moves and behaves in frozen and non-frozen conditions. They threw a tillage component in, a manure application component in, and a soil test phosphorus level component into their study. Multiple sites, multiple years involved. It's basically trying to look at the drivers of phosphorus loss, a major issue for water quality in frozen and non-frozen conditions. They basically had for this part of the study, they looked at runoff from a number of sites that they have. They had 10 days of surface runoff per year. They had basically about 3.15 inches of water per year running off, and they had 3 to 3.5 months of frozen ground they dealt with. So December through March was frozen. And then, but you also see in this graph, which is the annual surface discharge runoff inches involved, that March was the highest discharge point for water during the growing season. So water was running off of frozen ground. So the other way to look at this, and they did a lot of looking and a lot of parsing and piecing of data. So this is basically over the whole year. How does no-till and till how do they look in terms of surface runoff? As you can see in these bar graph on the left, very similar amount of water was lost in surface runoff between the two systems. A little bit less, a little tighter in the no-till, but still in the till, they're both shedding water. The interesting thing is on the right side is that in the no-till, you tend to see a lot less soil lost. So no-till does a great job of retaining soil. It doesn't change the water runoff that much in these conditions up in Wisconsin, but you see a lot less soil, 42 pounds per acre versus 205 for the till conditions. So it's doing its job in terms of soil retention. However, when you look at the phosphorus component of the water running off, you tend to find out that annual total phosphorus losses are pretty similar. In fact, no-till can be a little higher in terms of what's coming off those systems. So you reduce the amount of soil coming off, but the phosphorus coming off is almost higher in the no-till conditions. The interesting thing is it's actually a dissolved phosphorus that's leaving these no-tills fields, and that's actually what drives the total phosphorus loss. So no-till does a great job retaining soil. It doesn't do a particularly great job of retaining phosphorus. Now you have to be careful in this sort of making judgments on this, as the till is losing soil, which will also be losing retained phosphorus on the soil surfaces. So that's still a mix in there. We did not completely clear in these data sets. So you throw one more component in, and basically this is the frozen, non-frozen situation. So on the non-frozen side, total phosphorus is less than, total phosphorus in no-till is less, no-till is losing less total phosphorus than conventional. And then dissolved phosphorus, no-till is equal to conventional in these non-frozen systems. Now you go over to the frozen side, no-till is greater of total phosphorus loss, and then dissolved phosphorus is also greater in no-till in these frozen sites. So that basically, when you look across the whole year, your phosphorus losses are occurring when the freeze has has taken place for most of these studies. So that's an important discovery to pull out of here, is that the phosphorus losses we see over the year are basically occurring in these frozen conditions for the no-till systems. So it's during the frozen conditions, again, where no-till leads to greater dissolved phosphorus losses. This is an interesting set of graphs here that they also created. This is basically what happens if you put manure on late in the year. And what you find out is that with early winter versus late winter, manure applications, November through January for early winter, and then February, March for late winter, that most of your phosphorus losses in these systems will occur, especially as part of the total phosphorus loss, will occur in the later part of the winter. So if February and March manure applications have a much more significant impact on loss of phosphorus than do earlier in the season. And that's sort of summarized here, where in non-frozen, no effect of manure timing on total phosphorus or dissolved phosphorus. And in the frozen systems, the later the application, the greater the dissolved phosphorus and total phosphorus lost. So to recap this little bit of work out of Wisconsin, there's no difference in total phosphorus loss between no-till and till. The differences occur because of greater dissolved phosphorus being lost during frozen conditions. Manure, the greatest P losses occur when manure is applied late winter, February and March, and incorporation is an important part of reducing phosphorus impact, but it's only if it can be done without increasing soil losses. So you have to be a little careful on increasing the amount of material lost in terms of the tillage applications. And then, which we didn't cover in this presentation, but the 0 to 2 inch soil test levels are the most important variable driving phosphorus losses. So what's up on the surface is really important. So when soil test levels are higher than 93 part per million, you tend to see a little more potential for loss. And this occurs in no-till and with frequent manure applications. So no-till can be stratifying phosphorus a bit. I'm happy to answer some questions. Have you got any to be answered? Thank you. There we are. All right. So with that, any questions? No, not seeing any, hearing any.
Ron, I got a question for you.
Yes,
Is
sir.
there any thought of maybe the guys up in Wisconsin incorporating a cover crop into the study to see
Yes.
what effect that would have?
Yes, it's exactly what they're up to right now, is putting in the cover crops. So that is a ongoing project. The Discovery Farms program in Wisconsin and Michigan is a very, very active operation. And they're looking at, it's actually a wonderfully designed program, in my opinion. So they're doing all kinds of those kind of treatment situations. So cover crops, buffering issues related to edge of field, where do things move to, how do you manage the applications, creating zones for applications that are at distance to prevent things from happening, looking at sort of maximum movement capacities, those sort of things. But cover crops are a big part of that effort at this time. Yes. Other questions? All right, we have one more brief presentation. It's from Josh Ternary. Josh is Indiana Pork, and he wanted to provide a little bit of input on rules and regs related to animal manure applications. We just got this presentation from Josh recently, so it doesn't exactly fit the format you've been seeing, but we're going to show it anyway. Let me pop this open, hopefully. Here we go. And my name is John. So I will share the screen and we will get this going. Hold on one second here.
My name is Josh Trineri with the Indiana Pork Producers Association, and I've been asked today to present to you a comparison between two different rules that regulate nutrient management in Indiana. There are regulations for how to apply manure from confined feeding operation under IDEM's CFO rule. And then under the fertilizer use rule through the Office of the Indiana State Chemist, there are other nutrient application regulations for those who are applying CFO manure that's been distributed to them by the CFO operator, and also for commercial fertilizer. First, if your livestock operation is over these threshold animal numbers, or the operation has been required to for other reasons, you would have a confined feeding operation permit through the Department of Environmental Management. It comes with it some pretty stringent manure application requirements. These permits dictate how you conduct your soil tests, manure samples, and how you determine your application rates. Frequency requirements and size of sample requirements for soil testing are included in the rule. Specific requirements on how to develop your application rates based on your manure sampling data, and requirements for how and how often to get those samples are also included. As you plan those application rates, your limiting factor will be soil test phosphorus levels based on this chart, where any new application is capped at 200 parts per million. But below 50 parts per million, the application rate is nitrogen limited instead, dictated by these factors. In addition to rates, the manner in which the manure is applied is also regulated. Here's the setback table pulled from Indiana's 590 standard from NRCS, which has been codified in the confined feeding operation rule for those regulated facilities in Indiana. Application to frozen and snow-covered ground is also highly regulated. In fact, if your facility meets the federal definition of a large concentrated animal feeding operation, you cannot apply to frozen or snow-covered ground at all unless it's a pre-approved emergency application. Concessions are made for older operations with storage limitations, and those application restrictions can be seen here. I also want to highlight the specificity of the record keeping requirements under the confined feeding operation rule, especially as compared to the record keeping requirements we're going to visit in the use rule coming up. Next, I want to talk about nutrient application requirements for either manure that has been distributed away from that regulated confined feeding operation or for commercial fertilizer applications. Those are both governed by the state chemist fertilizer use rule. You'll note the nominal de minimis threshold here. The 10 cubic yards or 4,000 gallons. It's a small allowance so that, 4-H animals from kids' projects don't fall under these requirements. Staging restrictions are a big component of this rule because a major impetus behind the creation of the use rule to begin with was the lack of state authority over poultry manure coming into Indiana from out of state. A written application plan for fertilizer application is required, but record keeping requirements outside of that are very limited in scope. For example, monitoring requirements for 24 hours before, during, and 24 hours after land application manure and the confined feeding operation rule were required to be documented in records in the CFO rule. Here, as with many of this rule's requirements, the requirement may be here, but no formal record of it is required in many cases. Similar to the confined feeding operation rule, there are land application setbacks in this rule as well for the application of CFO manure, even though it's not that CFO operator that's land applying for his own use here. There are also frozen ground restrictions here, but they're more lax than in the confined feeding operation rule. Most notably, There's no prohibition for manure application on frozen ground from CAFO size operations. As far as record keeping outside that written application plan, records must only be kept regarding manure that has been distributed from a confined feeding operation or for applications made by licensed manure applicators. Basically, if you're a licensed applicator applying confined feeding operation manure or commercial fertilizer for hire, you must keep these records outlined here. If you're applying commercial fertilizer for yourself, outside of that requirement to have a written application plan, no other record keeping requirements exist. I hope this brief comparison of these two regulations was useful. Thank you for the opportunity.
All right. I can't answer questions for Josh, but we can certainly get into them if you have questions. Anyway, I'll put Ben on the spot and tell him he can answer the Josh Ternary questions. Are there any questions on this? Okay. Any other questions?
You know, I'll make a comment,
Okay.
Ron. It
Thanks, Tom.
seems sort of strange to me that, you know, you have to stay 50 feet away from a well, but you only have to stay 25 feet away from a sinkhole, which is an open hole into the ground. And
That's a good
if
point.
you've got anything moving, I mean, it's going to go down in that hole, and who knows where it's going to show back up again.
That's a really good point, Don. I'll ask about that. That's a good point, because you're absolutely right. Sinkhole is much more susceptible. A properly constructed well would be pretty protected from things on the surface. So assuming it's properly constructed, there's a lot of variation in that statement. So other questions? Thanks, Don. All right. Well, I think our time is at end. I'm happy to see you all here. We'll get the announcement out for our next presentations, which will be next month. Again, that'll be on soil health specifically. We have some discussion of soil health measures. We have discussion of some enzyme work, which is a little interesting. People haven't seen that before. We've got some stuff on aggregates. I mean, we got a lot of talk in terms of soil health. We're going to hear from Joe O'Rourke, who's our soil health expert in the state of Indiana. So that'll be part of the presentation next month. So we'll get that information out to you as soon as we get it all set up. So thanks for joining us today.
Thank you.
Thank you.
Aye.
You guys have no place to go. Is that your problem?
Oh, no. Just checking in to see if you needed anything else.
No, I think I've learned how to use Zoom now. Thanks.
So at 7 o'clock tonight, when Sarah and Linda aren't there to remind you, you'll be fine.
I'm overeducated now in the Zoom world. So videos look okay.
I thought everything looked really good.
Jason's for me was really grainy, but I could hear his voice very, very well. So it wasn't like I couldn't understand what was happening. So I'm not sure if others saw the same thing.
I think some of this results from how they get shot and the kind of camera they use to make the videos, because Jim was shot on a pretty high-end piece of equipment. Mine was on a fairly decent camera, and then I don't know what Jason used. So
He probably just used his own home computer, right?
Yeah, probably. So that's always a bit of a problematic situation. So
because I was on my showing end, how did the ones compare the last month that we made? Did they show similar to Jason's, or do you remember, you guys who were on the call? Like, were they more?
I didn't notice yours being grainy at all.
Oh, you weren't grainy at all, Sarah. So
No, yeah, mine was same. The resolution on Jason's wasn't as good, but the
Well, I was wondering
the audio was there, but just the screen resolution wasn't as
Great.
as
Well,
good.
maybe we'll want to like just check that before uploading it. I guess that's my only
Okay.
suggestion.
sounds like a plan, kids. All right.
Good job. Interesting
All right.
stuff. Thanks
Talk
for
to y'all later. Thanks.
Sounds good.
Yep. Nicely
Bye-bye,
done.
everybody.
Talk to you later. Bye.
Thanks.
See y'all.